Multilinear, and Sumcheck. So any questions you have, this is the time. Any approach that doesn't make sense, this is the time. And then you compare it with what you have, for those that have, and you see if it aligns, okay? And if there is like a better way you could do it. Then we'll benchmark also. We'll benchmark time, and we'll also benchmark operation count. So the operation count is more universal, right? Because we have different PCs and different PCs have different specs. So benching time, we can't really compare that, right? But we can bench like the amount of operations that we do, like the amount of additions we do or the amount of multiplications we do. So that way you can use that to kind of like gauge how good your system is. Because like field addition is cheaper than field multiplication. So usually you want to do more additions than you're doing multiplications. Then you can compare your counts with every other person's counts. You're all doing the same thing, right? It's still partial evaluation, it's still sum check. So if there's a difference in the counts, the person with the smaller count is probably doing it more efficiently, right? So this is like a good way to kind of like gauge efficiency. Yeah.
What extent is multiplication better than addition?
You can benchmark that.
Because let's say we have something that's more of this. I just do something plus.
Yeah, but that's like multiplication is not doing more than 1 plus, right?
Yeah.
So it's like 1 plus compared with multiplication, which is like, let's say like 2 plus 5 and 2 times 5. That's like you're doing 2 plus 2, 5 times. This one is just 1, while this one is 5 additions. So that already shows you that multiplication is already like slower than that addition because it's doing 5 times the work. Make sense?
Sorry.
Yeah.
Are you going to show how to install the benchmark?
Yeah, we'll benchmark on
Like
this.
you show how to install it.
Yes.
Yeah, we'll do that today. We'll do that today. Bruh. We have to make sure that entropy does not seep in. Because entropy, that's like we don't get comfortable. As we progress, it's getting harder. It's not getting easier. So we're supposed to be more like on our feet than people should be coming early and should be ready. Because GKR now, imagine you don't come for the first 5 minutes. You are probably done for the rest of the class. You literally have to go back and watch the entire video. Yeah. No, we will fix the entropy thing. We just have to. I'm just like letting you guys know. It's getting harder over time. So after GKR now, probably go into Fry and we'll go into Binios. And those ones are crazy. Sumcheck is child's play relative to all those other things. Yes. Sumcheck is child's play. It's child's play. I cannot come here and implement GKR for you guys. Doesn't even make any sense. Like it's just too wide for me to try and implement it. So, but Sumcheck now, I know that okay, yes, we can still implement it.
But with the time for implementation
Yeah, it will be longer. The GKR time for implementation will be longer.
So after ZK, is there another devil up front?
There are multiple devils up front.
That GKR is not child's.
Huh? They'll make GKR child's play. Not really. Once you're done with GKR, you're kind of like a new person at that point.
So is it DKR?
So quickly. GKR.
He know the wine.
I go into this so.
Now you will give us this.
Now you will wait for.
Thank you.
I'm very grateful.
Alright. Let's start. So we'll do multilinear first. That's good. I'll do everything in one file rather than using workspaces.
Alright.
Okay, let's begin. So, okay, I'll try. So most of you guys that'll be driving this actually. I'll just be writing what you're saying. No. So not multilinear first. So let's start with the representation of multilinear, right? Evaluation form. So what would that look like potentially? An array of field elements, right? I don't know, the last time we did this implementation, did we use F64 or... I don't know if I used field last time I did this. I used field?
No, you did it first, then you converted it to
I didn't.
It was Francis.
Oh, Francis did it. Did you push? You didn't push? No, don't worry. I'll just do this now. It's ArcFF now. Right? Okay, so let's create a struct. Can you see it? Can't see it. You don't trust him. Can you see it? Are you sure? So let's call it evals, right? Prime field, I guess. Okay.
So it wasn't the public.
What? You could. Yeah. If it's public, then that means you are expecting it to be used in another, which is the case for you, right? Because we have different crates. But me, I'm just putting everything in their separate files, so it's fine this way. Okay, I don't know if it sees this thing yet. Okay, so we're good now, right? So we have the rep. Now that I have the rep, what do we want to implement? What methods are useful to implement? That's for transcript, right? So we'll come back and do that one. So eval, partial eval, what else? Huh? Yeah. We'll see, yeah. So that's just like sure. So evaluate, what is evaluate taking? In itself, right? Like it needs access to the evaluations.
Yes.
And then it also needs the points that you want to evaluate at, right? So what do we call that? I'll just call it assignments, right? Assignments to the variables. This is basically like a collection of field elements, right? And we're returning a field element. So I'm just going to do some sanity checks, right? Like the number of assignments must be equal to the number of variables. But we don't know the number of variables. How do we know the number of variables?
You can know from the number of the number of events.
Yeah, so we can also pass it. So let's do this.
If you are passing it, why not manually do that?
So I'll create new, right? I'll have like the number of variables. And then I'll have like the evaluations. Vector
But you
vec.
can complete the number of variables, right?
Yeah, I can.
Inside, like that, those are the functions.
Yeah, but I don't want anybody to create a multilinear polynomial that is not a power of 2. You get? I don't want to ever get to that point so that my evaluator doesn't have to think about the fact that the user might not have instantiated it correctly.
Yeah,
So-
but if you do it this way, you can just panic now. If the person
Yeah, like a check.
But then I'll have to do it on all my functions.
no
Evaluate,
at the point of
partial
creation,
evaluate,
at the
add
point of
new.
creation, yes.
And that's why I'm creating new. So that I don't allow that creation to happen. Via, let's say,
I'm
the
saying that
panic.
we can do without passing in
Yeah,
number of
exactly.
variables. Because this way now, they'll need to like, when they are evaluating, they'll need like, now know the number of variables.
Yeah.
But if it's just like, without the number of variables, you can just complete based on the already passing, you can just complete.
So you can use the
And then you check if it's like
Yeah, if it's
a
valid, yeah.
valid means that there'll always be log base 2 or something, right? So you're checking if it's like not a real number, like if it's an integer, right? Yeah. That works. That works. Who am I? Okay. So how do we do this? This is the same thing as 2 to the number of variables, right? There's power of 2. Yeah, you can do that. But now I want to actually like compare it to the number of variables itself. Okay. And then I'll just store it here also. So I don't have to be computing it. It's not expensive to compute it though, so it's fine.
I used to take in the number of variables for you.
Huh?
I used to take in the number of variables for you. But I wanted to remove it.
No, I'm taking it in.
Huh?
I'm taking it
Okay.
so that I'll just use it just to make my life easier.
So what are they using?
Huh?
What are they?
NeoVim. So we're good, right?
So this last line now.
Yeah.
This one is updating that struct, right?
I'm creating the struct.
Or is it just returning?
Yeah, returning
itself?
itself.
Yes, yes. Like, is it updating the structs, the
This?
values in the struct, or is it just returning itself?
So this is not a concrete type. This is just a type definition.
Yes.
So like it's not a concrete thing that
Those
is updatable. Yes.
Okay.
So this is where I'm creating the first concrete version of that.
Yes. With values.
Yes, with values.
Okay, so that means that it's just returning it based on when it's called.
Yes. Does it make sense?
I don't know why you use this inequality sign.
So I'm saying if the evaluation dot length is not equal to 2 to the number of variables, you know, like let's say you are doing 3 variables, then you're supposed to send an evaluation array that has 8 elements in it. That's 2 to the power of 3. So I'm ensuring that the number of variables matches the evaluation line.
Well, you know that 2 to the power of is like 2 to the power of the number of variables. It's like 1 to it says that.
No, I'm asking for the sign specifically.
It's not equal.
It works.
How did you get that?
Oh no. It's no, that's not what it's talking about. So see, I put none.
Oh, is that the ID that
The ID that changed. Should I change to Rust Rover?
That's what I just did.
That's what I just said.
Huh?
That's what I just
Still
did.
do it.
Oh, you see, this is
Yeah,
it.
yeah. If you are using, I think,
Except you are using VS Code.
But does that sign work?
No, it won't, the compiler won't see it like that.
Okay.
This is better, right? Okay, let's use this. So now we have new, and new forces the type to be created properly. So now anything that sees a multilinear poly is comfortable. It knows that okay, the number of variables matches the evaluation. So I don't need to do all those checks in any subsequent thing that uses multilinear poly.
So how about if someone is putting in 8 5 of 8 lengths and mistakenly puts like 2 number
Yeah,
of
to panic. Yeah.
What would it
You're saying that the number of variables is 2, but then you're giving me 8 values. It doesn't align. I know you don't take the number of variables right.
I'm just thinking.
Power of 2, that's what you care about.
No. That's my mistake. If you are
And if you mistakenly, then we'll tell you that you put the correct thing back.
So you want the length of evaluations and the inverse to be the same.
Yes.
This is not.
And 2 to the
two
number
raised
of
to the
us.
power.
No, that one shift
It's
is 2 to the raised to the power of something. Let me show you. Okay, so see now. Let's say we have equals 3, right? Then I dbg 1 shift a. I'm expecting 8.
So you want the inverse to be 3 and
No.
the length to be 8.
In this case, yeah, inverse is 3. Then evaluation length is 8. Yes. Yes. Because every time you left
Okay,
shift,
variables. Okay.
yes. Every time you left shift is multiplied by 2. So if you left shift 3 times, you're multiplying by 2 3 times, which is like 2 to the power. Yeah.
So the right shift is divided by 2.
If you right shift is divided by 2.
What knowledge of this base manipulation do we need?
As many as you can. Because there are ways to do without it, right? And there are probably some things that I'll do that I'm not using it that I could have used it. So if I had more knowledge, I would know that I could use it there.
Which one is better? To do 2 times 2. Like normal multiplication.
No, bit manipulation is always faster. Because there's always one CPU cycle. Multiplication might now need to think about like overflow and all those things. So that would require more like cheap machinery. Oh,
So meaning that this is better than.
but this is good, right?
So this is better than if we say 2 power of 3. No, that's inbuilt power in this.
Yes,
So
but
is this better than when we use that power?
yeah. Power is doing more than shifting. This one is like we know that it's going to work. So we're like, you don't need to do all those extra checks and all those things. Just do it straight. That's where you get the efficiency. Does it make sense? Okay, so let's go to evaluate now. So for evaluate, we're going to use partial evaluate, right? So we just call partial evaluate multiple times. So but there's a constraint. Sir, bless you. The assignment length is supposed to be equal to the number of variables, right? You're supposed to have one assignment for each variable. So we'll just be like, if assignment dot len is not equal to self the number of variables, then just panic, right? Like, what are you doing, right?
So, I'm going to this one. It's still fine.
Why would you panic?
Like when you run, it's still but it's still something like it's like
Depends on your partial evaluation code. Yeah, it might. Yeah. Normally, you're supposed to actually return proper errors, though. Like this is, I just don't want to stress. You're supposed to return proper errors. So this is not going to be like F. It's going to be maybe like a result that is F and some error term. So instead of returning panic, you do like return error. Then you just like write your error here.
If you panic for now, we can complete.
Yeah, you can update it here. I'm just choosing the thing that will give me the least amount of stress. So now that we're done with this, depending on how we implement our partial evaluate, we can write this differently, right? So I'm just going to assume that partial
So
evaluate.
if assignment is assignment not the array of like that 16 different points.
No, so let's say our polynomial is 3 variables, right? So A, B, C. Assignment is just what's the value for A, what's the value for B, and what's the value for C. Depends on.
Oh,
Depends on.
that is the index. That's
So let's say you had something like this, right? F of A comma B comma C, right? Then if you evaluate at like 3 comma 4 comma 3 comma 2 comma 4, 3 comma 2 comma 4 are the assignments.
Oh, okay.
Then it's not give you the results. It's just the points you're evaluating at.
Okay.
Makes sense, right?
Yeah.
So what do we want to do? We want to like partially evaluate the assignment multiple times. So for there's a better way to do this though. There's a better way to do this.
Is it the y1 plus?
No. This is so painful to do. So we'll call partial evaluate, right? How does the partial evaluate work? You pass in the variable and you also pass in the value.
The evaluation point. The index and the value.
Yes. So the index is always going to be 0, right?
Yes.
Then the value is going to be the value, right?
Yeah.
Then we update the polynomial, so it's now a smaller polynomial. And then by the time we're done, we should have a polynomial that has just one value. For ABC. Yeah.
Sorry, the index being at 0,
Yeah.
mean that like you have to evaluate one thing.
Yeah, so
You can't just pick anyone. Like, you can't just evaluate the. You got ABC now, 2 to the answer, and I'm probably going to evaluate and only
that's partial evaluation.
Yes.
Yeah, this one we're doing is full evaluation now.
Yes, what I'm saying is that should be partial, like, you have to partially evaluate at, like, if you have ABC now, you probably have A is 2, B is 3, and C is 4. And I want to evaluate my B first. And you know that my B is an index of 1. Yeah, now you're passing 0.
Yeah, but if you want to evaluate your B first, you shouldn't be calling evaluate. Evaluate is like you already have all the assignments for A, B, and C. If you want to evaluate B first, it means that you maybe don't know what A and C is yet. So you just call partial evaluate directly. And instead of passing 0, you're passing 1. But because we're doing full evaluation and we have all the values, then we get rid of A, we get rid of B, then we get rid of C. Does it make sense? So now that we have the final poly, we just return like the poly dot evals at 0, right? Because it should be only one thing that's left there. Does it make sense? So we're done with evaluate, but evaluate should not work because we have not implemented partial evaluate, but at least we know what the structure looks like. So now we do partial evaluates. So partial evaluates take the index, and then it's to take the value. It's to return self. Thank you. And it's going to return another polynomial. So how do we do this? Why is this complaining? Yeah.
First time borrowing. Or maybe this has not been created.
It somehow it thinks that this is
assignment just without enumerate and then get their index.
Sorry, I'm coming. It just doesn't know that there's clone there. Yeah, you said?
Like, all I'm trying to get now is the index.
Which index? In evaluate?
That's
In partial evaluate. Okay.
Like, in the evaluate, like the partial evaluate.
This 0. It's always 0. So it's, the idea is that you have f of a comma b comma c, right? And you already have all the assignments for a, b, and c. So once you use partial evaluate to do full evaluation, so what we'll do is that we'll evaluate a first, which is at index 0, right? But then when we're done, a will have disappeared, and we'll have a new polynomial that is just f of b c. So the next one we're going to evaluate is b, but b now is at index 0. I don't know if that makes sense. I don't think that would make sense.
So you're trying to put 0 here to like have that graph.
Like it's always.
Be retaining its index and all those assignments in their index, right? why 0 is there? So that they will maintain the index.
So it will maintain the index.
Like that. Yeah, index is like, because if A disappears and B becomes
0.
yes.
Then the next time it's also to be 0.
Yeah.
Yeah, just consider that.
Because I'm trying to think of how I did mine. Because I didn't use 0, but I think I increased the index.
Increase the index.
Like I did +1, like instead of.
So are you partially evaluating multiple variables at once? One at a time?
Yeah.
So how is +1 working?
Mine, I always use like the evaluate and all that.
Okay.
I didn't like anything I want to call will always be evaluate. So I could pass in maybe a sum like an option, right, for each variable. So if I was evaluating B, my array size would still be 3, but only B would have like a sum value and the rest would be none. So I'm basically like counting how many have been done. So say I have like A, B, C, right? If I'm evaluating 3 of them, I'm still using the index of B, but I'm just subtracting how many have been, like how many variables I've evaluated before B, and pass that as the index.
But what if you're like evaluating everything at once? Like everything was sum.
Yeah, that's what I was saying. Like if I do A for example now, right? A goes, and then my done increases to 1. So that means I've evaluated like one variable. So that means the index of B is 1. I'm just subtracting that index from the number of like.
So that would change to 0, right?
Yeah, that will change to 0.
So you're still putting 0, but you're doing the
exactly.
calculations. Okay. So this is like you have f of a, b, c, right? You want to partially evaluate a, the index is 0. Let's assume I now partially evaluate it. I'm going to get a new polynomial f of, right? Now I want to partially evaluate b, the index is still 0. And then f of c is still 0. So I can just like fix it at 0 and then be done with it. But like my actual implementation, my partial evaluate can partially evaluate multiple at once, which is just like more efficient. So I don't have to do all this like clones and all. But it's fine for now. We just want something that works.
So can you communicate what you just said?
My actual partial evaluate,
That you would
yes, not this one, takes in not just one value. It takes in a starting index, but it takes in a vec of assignments at once. So I don't need a for loop in my. Well, the for loop just moves into partial evaluate, technically. Yeah. It's just like an API stuff. Okay, so partial evaluate, how do we do this? What do we need to do partial evaluate? This is like the meat. Yeah. We need to somehow pair. We need to generate the pairings based on this index. Right? The index is what will tell us what the pairings are going to look like. Then once we have the pairings, we can now use the value and the pair to compute the next array, right? So it's more like use index to generate pairing. Then when we have used the index, now do like linear, right? And that's all. This part is easy. This part is also easy, but it's confusing if you need to think about it. So let's work on this. Let's assume the interface actually, and then let's just. What would be a nice way to have this? So if the index is 0, then that means that you're evaluating A. If the index is 1, it means you're evaluating B, C, D, on and on like that. So the approach I want to do is you use Boolean hypercube of a smaller Boolean hypercube, and then you insert the bits where you need to insert the bits. So let's say you wanted to generate like for A, it starts with 0, 0, 0, 1, 1, 0, 1, 1. Then you give 0, 0, 0, then 1, 0, 0 for A, right? So we're adding the bit 0 here, and we're adding the bit 1 here, but then we just repeated the 0, 0, 0, 0. Then this one will be what? 0. Yeah. Yes. So then this will just be like my pairing automatically. So we need to figure out a way to do this in code. What I really love is like an iterator that just iterates and gives me tuples. right? Like, so the iterator will give me 0, 0, and 1, 0, 0, but not as binary, as actual number, because this is a number, right? 0, 0, 0 is just like 0 and 4, and then this one is 1 and 5. So I don't want the binary. I want the yes. So let me just try and like see what the interface might be. So I'll be like for, let's say a comma b. A will be like 0, then b will be 4 in something. Let's say call it like pairs or so. We'll fill this in later. So what do we want to do with the pairs? Let's now assume we have the pairs. What do we want to do with it? Interpolate and evaluate, right? But we need to like store the answer somewhere, right? So we're going to push, right? This is so inefficient, brah. But it's fine. So we're supposed to take A. This is like y1, and then this is y2. So we're supposed to take what? Y, that's B.
No.
A. Cool. So now that we're done with this, we should be able to create a new so what will be the new number of variables? So we want less, right? Because we just partially evaluated 1 point. So the number of variables will reduce by 1. And then the coefficient is going to be the result. So once we're done with this, we have partial evaluate. So all we just need to do is
Is this supposed to be safe
nvars. Is it this one?
because inverse remains 3. This is 3. It keeps on remain 3.
No, minus 1.
So I'm doing -1.
Yeah, you are doing -1. Like first is 3 minus 1. Second is still 3 minus 1.
No. So see, in my evaluate, right? Whenever I partially evaluate, I store the results in poly.
Okay.
So this original poly was 3 variables. Then I did a partial evaluation. It got me a new poly that is now 2 variables. And then I put that here. So next time I call partial evaluate is with 2. So it's just reducing, strictly reducing. Makes sense? So then this is the hard part, right? Like, how do we do the pairs? What is this supposed to even take? Is this enough?
That's tricky, I guess. Depends
It's like,
depends on
most likely, yeah. So I'm trying to say, like, what do we need to be able to compute the pairing? Like, what information does the pair function need? Like, it needs to know where you want to insert, right? But it also needs to know the size of the pairs you want to generate.
Sorry.
So let's say 3, for example.
It's A1, it's A and B. Like,
Yeah.
and they basically like the Y1 and Y2 value. Not the index now, right?
It's the index.
Okay, I found
So-
this on the web for us as a what?
So you found a bug, right? Like, A and B are indexes. They're not the actual value. So we cannot just be doing this, whatever we just did here. So instead we need to get it.
Yeah, does enumerate will give you the index.
But do we need the index?
You can just return the value.
Huh?
I think done is okay.
Yeah, this is going to work by returning the index that's 2.6, 2.7.
I don't know if you call pairs will be called
It will return the tuples, but the indexes. So in this case now, it will return 0 and 4, 1 and 5. But then that just means that we need to actually pull the value at 0 and the value at 4 before we do the computation.
How do you put that pairs?
But that means I have to pass off inside pairs,
Okay.
which is doable, but I don't like it. But it might work actually. Let's fix it here first. Then so what I'm going to do, solve the what? Oh no, this is all Okay. So this works, right?
Yeah.
So now we're getting the actual value. So I just shadowed it so that I don't have to change all those things there. So pairs. It needs the index for sure, right? It needs the index. We know it needs the index. So if it's 0, then that means like we're evaluating A, right? But at the same time, it also needs the length of the hypercube. That's the target hypercube, right? That's based on what the number of variables. Yes. So what we can just pass here is like the index, which is the index, and then solve the number of variables. I think this should be enough to generate the pairings. Does it make sense? So let's now implement pairs. I'm just going to implement it outside of the function itself because it's not really like a multilinear. So it needs the index and it needs the number of variables. Then it's going to return okay, so I could have just returned vec actually. I just vec of tuples. But this is the preferred way, sha. Let's just
Let's
consider.
see the return type.
Return type is saying that return to me anything that I can turn into an iterator of tuples. So that means that you don't have to like use a vec, or you don't have to. It's not compulsory, right? But I don't think that's necessary now that I think about it. Like I could have just done like vec of right. But then what that will mean is that when I'm here, I'll now need to do But if it was the other one, I won't need to do that because it's already like. I have multiplication complaining. I'll fix it later. Okay, so now pairs. How do we do this? We know the number of variables, right?
Yeah.
So we can get the number of variables for the smaller. So you know, like we start with 3, then we can know that it's like 2. So when we know that, what do? We need to now iterate over every element in that smaller hypercube, and then we need to insert the bits at the correct spot. So before we do all of this, let's first of all implement the insert bit, right? So it takes a value, and then it takes like an index that you want to insert the bit at, and then it gives you a new value. So this means that if you have something like 4, no. Let's say like 3, I want to insert at index 1, right? We'll call something like insert bits with 3, and we also need to tell it what to insert, but let's just assume it always insert 0. Okay? Because there's a way to now make it 1 easily. We'll go over that. But then 3 is what? 3 is 1, 1, right? So when you insert 0 at index 1, it's going to be 1, 0, 1. So this is what we're expecting. We're expecting something that can do this, essentially. So the way we did this was that we broke it into the high bits and then the low bits, and then we put the thing we wanted to insert in the middle. Yeah. So let's get the high bits. So the high bits is going to be at the point of insertion, you break it, and then everything to the left of that is going to be the high bits. and everything to the right of that is going to be the low bits. Okay? So how do we get the high bits now? It's right shifts.
For masking.
No, not masking now.
We want the high bit.
We want to get the high bits. So we want to remove everything at the end of it.
So let's say we had 1 1.
We had 1 1, yes.
Then we want to remove
That last
the
one.
It's supposed to be and
You right
One
shift.
right.
okay. Oh, I was doing like and 1 0. So it will cancel.
It removes it by turning to 0. Yes.
Yeah.
But how will you know the 1 0?
Left shift by the number of.
You're actually 1 by the number. That works. Yeah, that works. That actually works. Yeah, that works. That works. It might be faster, in fact.
So high bit is
High bits. So let's say we had like 1 0 1 1, right? And then the high bit is like 10. Let's say we wanted to insert at this point. So what we can do is that we can like right shift twice. Right? So when you right shift the first time, you're going to get 1 0 1. Then when you right shift the second time, you're going to get just 1 0. So that's it. Then you are suggesting that instead of doing that, we should and it with what though?
And it will. Oh, yeah, exactly. 1 0 0.
That's not enough. You need like 1 1 0 0.
Oh, yeah. Where's
Yes,
the initial
actually.
one?
So how do you do that? Like everything has to be 1, right?
Yes, on the other side. I think there is this few. I don't know. I'm not from how it goes, but I saw this few with starting ones. I saw it somewhere.
Okay.
Something like that.
That's
So
just
if you left shift it, then you can specify the length and fill it with.
if you left shift it.
Like you want 1 0, right?
Mm-hmm.
Since you want 1 0, take it down, left shift it twice, right? After left shift it twice, it's go to the 1 0 0. But we want the
If you left shift it, you're adding zeros to the back row.
yeah. I'm not left shifting this.
Okay, left shifting.
That one.
Oh, okay.
Yes.
Then you now fill it up with just
It's
1.
one.
Okay, I get what you mean. Alright. Let's just continue. So how do we know the amount of bits? We need to know the length of the low bit, right? To know how we would shift it. So how do we know the length of the how do we know the length of the low bit? To make it easier for us, we can assume that the index is working from the back. Right? So if you're inserting at 0, then you're just going to insert at so let's say you had 1 1 and you wanted to insert 0, like it's going to turn into 1 1 0, right? So the index is actually telling us like from the back, right? If you wanted to insert 0 at index 2, then it's going to be 1 1 will turn into. You get? So we're going this way. So this means that this index is already kind of like telling us how many we should shift, right? So if the index is 0, it means I want to add at the back. That means we shouldn't shift at all. So that means it's safe to just shift by the index. If the index is 1, we're supposed to shift once, and then that's the high. I don't know if that makes sense. So I let high be equal to like value. I think it should work. Then now we need the low. So low is just like
Sorry.
yeah.
So when you're calling like instead, for example, let's say you want to do for B,
Yeah.
right now. So what you're saying is you're passing in maybe number of variables minus.
Yeah, most likely, yeah. So that it will reverse. But we'll check. If it doesn't, if the API above doesn't allow, then we'll have to come back and change stuff, but hopefully it does. So now for the low, we need to do the mask. That mask thing. Where like we just and with ones at the place. So let's say we had like 1011, right? I wanted to get the last two. So we just and it with 0011. So the question is like, how do we get this like 0011? So what you could do is that I think you could left shift 3 times and then subtract 1. So like if you left shift, I say 1 left shift 3, that will give you what? 1. Yeah, so I'm thinking it should be left shift 2. Then when you now subtract 1 from this, you're not going to get right? So the question is like, how do we know this 2? Let's say you're inserting an index 0, index 1, index 2. So I think the index is still also the 2. So let's just write it fast and then test it, because all this ones, until we test it before we actually know whether it's working. So we get the mask first. 1 shift index, then everything minus, right? Then what we do is just do value ampersand mask. So now we should have the high and we should have the low. So now what we need to do is combine them. Yes. So want something that has like the high here, then the new bit here, and then the low here. So this means that we will need to create space for the low and the high. So this means that we need to shift what? We need to shift the high. We shift it by 1 first for this new bit right here. But then also need to shift it by low. So that's what we need to calculate. We need to calculate whether index is enough to so what is index? Index is the size of low, right? Yeah, setting an index 0, there's no low. So we are setting an index 1, there's 1 low. And setting an index 2, there's 2 low. So we need to shift it by 1 plus index, yes. Then we OR it with 0. Yeah, we're about to do low. So like we have moved it high now. Now we're supposed to put the new bits. But since it's always 0, I think it's fine. We don't need to do anything again. So all we just need to do is OR it by low.
Have we added
New bits. So it's always 0, so there's no need to add anything.
Okay, that's
Yeah, we made the assumption that it's always 0. So let's test this, because I don't know what we have written. Right? So we call insert bits with the value. Also wanted to insert into 3 at the back. So then we're expecting 3 is 1 1. If I start at the back, then it's going to be 1 1 0, right? So 1 1 0 is what? 5. So we can just write it as binary, so that we're not confused. That error that we had the last time, let's come back to on us. So value is what? Value is we could do this. I don't know if this is sufficient though. So it passes for 0. It passes for 0. Let's now insert at index 1, right? So this should fail. Yes. But if I insert at index 1, that's going to be what? So we started with 1, 1, right? Then we're just inserting a 0 at index 1. Then instead of 1, we're inserting a 0 at the beginning, right? So it's going to be like this. So all of this should pass. Okay. So that means our insert bit works properly. So now that our insert bit works properly, we're supposed No, they wanted us to get it, they wanted us to make it work first. And then, so the idea is that we want to create something that can insert a 0 into a binary number. Alright? Yes. Okay? Does the program make sense?
Why should we, my question is, why should we insert 0 plus 1?
No. So when you insert 0, you can easily get once you insert both 0 and 1, right?
Yeah.
So I'm creating something that inserts 0. You see how many steps we had to do just to insert 0? I don't want to have to do that for 0 and then do the same thing again for 1. So what I'm going to do is I'm going to insert 0 first, then I'll modify that 1 to insert 1. So like let's say we had like 1, 1, and I inserted 0 in the middle. So that'll be 1, 0, 1 through that complicated machinery. In order to insert 1, I'll just OR it with 0, 1, 0. So I'm ORing it with 1 at the mid. So that will now give me like 1, 1, 1, which is exactly the same thing as inserting 1 at that location. You get? So that's why that function is only inserting 0. So like now we only need to do like one operation and we've gotten the other side. So I'll probably need to rename it to like insert 0 bits. So but how we are inserting it is that we figure out the point we want to insert at, right? So let's say it's in the middle. So we need to somehow get this it's into the left of the point and it's into the right of the point. We call this one the high and we call this one the low. So we've split them up, so high is here, then low is here. Then what we do is that we now shift high, low plus 1 times. The reason we're doing that is so that we can create room. That plus 1 is to create room for the new bits that we're about to insert. So in this case now, low has just 1 item, right? I want to add 1 new item. So that's going to shift it twice. So that will be 1 shift 2, which is going to be 1, 0, 0, right? So technically 0 has already been added for us. So all I just need to do is I just need to OR it with the low, which is 1. And at the end of it I'll have 1, 0, 1. So let's do like a more complicated one. Let's say we had 1, 1, 0, 1. I wanted to insert it at this spot here, right? So what we'll do is that we split it into 2, right? So high is going to be what? Right? Low is going to be, right? Then we need to shift this at high plus 1, then low plus 1, sorry. And low is what? 1, 2, 3, right? Plus 1, that's 4. So that's going to be 1, 2, 3, 4. That's been shifted. Then we just OR it with low. So it's supposed to be 4, right? High shift 4. Then we OR it with 1, 0. Does it make sense? And you can see that we have inserted the. Then if we want to add the 1, we just OR it with and we're good to go. Cool. Then the code just does what we did. So the high, this is how we get the high. We like left shift to delete the low completely delete the low. So index is the same thing as the length of low. So we write shift low times to delete all of the low. So we'll just be left with high. Then this mask is to get like low number of ones. So let's say I want to get 3 ones, then index will be 3. I want to get 4 ones. So basically this is just like low number of ones. So when we AND something with just ones, only the place where there are ones would remain. And since we only did low number of ones, only low would remain. So this is like high and low. Then we just did what we did now. Like you shift is low plus 1, and then you do it low. Make sense? So now that we have insert bits, we should be able to do pairs. Hopefully, we should be able to. I don't know if this will actually work. So we want to iterate over the lower hypercube. So the number of variables is 3. We want to iterate over 2, right? So that we can now insert the bits at the appropriate spots. So let's say like target HC is going to be like number of variables minus 1, right? And then we now do for I in 0, 1. What I just did here is like so let's say we're starting with 3. If we're starting with 3, then our target H2 is going to be 2, right? I need to iterate over every possible value in the 2HC, in like the two variable hypercube, which is basically 4 elements, right? 0, 0, 0, 1, 1, 0, 1, 1. And then to get the number of variables there, just like 2 raised to the power of the target HC. Does this make sense? So let me just like example. So let's say 3 variables, right? That's where we want to get our pairing from. So the target HC is going to be 3 minus 1, which is equal to 2. But then what we now do, like we iterate from 0 to 2 to the power of 2, which is basically the same thing as iterate from 0 to 4, right? We're going to generate 0, which is the same thing as 0, 0, 1, 0, 1, 2, 1, 0, and 3, 1, 1. So it generates the hypercube for the lower dimension. Does that make sense? Then when we're done with this, we'll now insert the bits at the appropriate spots to get the target system out. So here, this I represents 0, 0. Then next time this represents 0, 1. Then 1, 0. And then 1, 1. So if there are any questions, please don't hesitate to. Okay, so now, what do we do? So this index here represents from the front this time, right? Because it's coming from, where is it coming from? It's coming from here. Like if we're partially evaluating A, that's going to be 0 from partial evaluation point of view. If we're partially evaluating B, that's going to be 1. But then our insert bit is doing it the opposite way. So we need to subtract from the number of variables.
Can you go back to your place?
Minus 1. Oh, okay. So let's say we had 3 variables. Sorry. We wanted to insert a bit here. What will be the index? So by inserting here it will be 0, right? By inserting here it will be 1. So it's 2. So how do we get 2 from 0? So that's like the number of variables, which is 3, minus 1 minus the index, right? Which is I in that case. So that's minus index minus I, minus 1. Okay. So what does this mean? It means that the first one is going to be called insert bits. let's call this value instead. And then the index is not going to be the direct index. It's going to be the number of variables minus the index minus 1. That so that's like when we have inserted 0. So then to get the insertion of 1, we now need to OR it with 1 that is in the correct position, right? So that's like right? So we need to move 1 a certain number of times. So the question now is like, how many times are we going to move 1?
Number of loads.
They're like low plus 1, right?
You show what it was before.
Where? Okay, on the tab, right? So you see this now. We need to do the shift. Like this is supposed to be like 1 shift 3, right? But how do we get this magical 3?
Index minus 1. Oh, here we're starting at 3. Here we're starting at 3. Right?
So this is like 0, right? This 1, this 2, this 3. Yeah, we're starting at 3.
So maybe it's just like index.
By the index, right? Okay. We'll test it. Let's just write something fast and then we'll test it. But then the index is no longer the same, right? It's like so just to make things cleaner, let's just say like
Index.
yeah, you can do that. I think you just use index directly.
Yeah.
We'll test it. So now that we have this, we can push it into the results. Let pair. No, let me just call results. Just like a vector. Right? Then all we just need to do is just push. Right, and then we return the results. So let's test this. Let's see if it actually works. Or if there's a bug somewhere. So how do we test this? We need to call pairs with what? The index we want to insert. So let's say we wanted to insert at A, right? So that will be 0. And then the number of variables, which is 3. So we're expecting 0 should be paired with 4, right? And then 1 should be paired with 5, on and on like that. So if we do pairs 0, the first pair should be 0 and 4, technically. Yeah, in numbers. We can also do like okay. That's not that didn't run, right? It didn't run, no. But that passed. Let me just print out the pairs. This is correct, right? 0, 4, 1, 5, 2, 6, and 3, 7. What would B look like? So, alright. So for B, what's B? B is going to be 0 is paired with what?
2.
Okay.
Y greater than
4, 6, 7.
So this is what we're expecting for B. And that's index 1, right? You made the test? Yeah, I just want to print it out and see. It will fail, but yeah, it is. It's correct. I think it works. Let me try for C just to be sure. It's supposed to be like together, right? 0, 1. So we'll ask questions.
Yeah, I'm trying to remember the inverted index.
Yeah, because the insert bits, right? I'm starting from the back. So if you say insert at index 0, it's actually inserting.
At the back.
Yes.
Okay.
But then partial evaluate, whenever it says evaluate at index 0, is from the front, right? So A0 is at the front, but then when you're inserting it, it's at the back. So I need to invert it so that when I'm talking about A, it knows to be talking about 3 in the. So that's why I'm inverting it. But you know, it was easier for us to do the insert bit if we think about it from here, because we can easily get the length of low directly from like the index. You guys have your ways that you implemented pair, so you don't have to like understand it fully, but just know that you can do it this way technically. Oh, yeah. So we're good? So now we have the pairs. So we should have partial evaluate already now. Right? Yeah. Yeah. Does it build? It builds now. Yeah, it does build. Who has like a test for partial evaluate? Three. Okay, so that's like poly equals multilinear poly dot new, right? 3 variables. Then vec of what was it? 0, 0. Mm-hmm. So these are supposed to be field elements. So I need an actual field element. So what's the name of that library again? App something. BLS. ACK. Oh, nobody use BLS. Hyphen instead of underscore. Is that what it? I think that's what it is on the. And it works.
Yeah.
Malware.
I think it's up and down. There's underscore.
I see underscore, yeah. Yeah, I've installed malware, bruh. I think maybe it's the same thing. Like you just that'll be crazy. We can try for this. Let's try and install this, but with a mix of like underscore and. Right? So if this works, then. So the crazy IO just doesn't care. That's ridiculous.
Check your credit.
You must have studied the Polynomial format.
Is it though? Maybe remove it just
What is it there?
It used
hyphen.
Converted both of them to
Yeah, yeah.
So I think I see.
But they don't care. Since they just don't care. Maybe when see.
Maybe they use regex.
Yeah.
So cardinal cares, but Quate does not care.
So when you partially evaluate this polynomial, this is what 2a plus 3bc, right?
Yes.
2ab plus 3bc.
2ab, yes, plus 3b.
So what should we partially evaluate this at?
C equals to 3.
C equals 3, okay.
Yeah.
So I need to make this methods public.
What if you just use problem and use spreads inside?
Yeah, so if you not import it as a library, then other people can have access to that. But PubCrate, since it's not going to be a library, there's just no reason to. Okay, so you said poly dot partial eval. Where's my partial eval? At what?
Index
C
2
equals
equals
to 5.
to 3. Like C equals to 3.
So 2, 3, right?
Yeah.
This is not supposed to be field elements. That's why I installed that library, exactly. So use what? Arc bn254 dot. I use FR. I'm an FR guy. It's just different primes. So rather than doing like f dot or from all the time, you can just like do into eta dot map like v, then f dot or from v, then you can collect. Then you can also like create a function that does that for you, so that you don't have to write it multiple times.
There's an error.
I want it to just go to a new line so that I can see it properly. It's seeing it as I32 when it's not supposed to be. How do I force you to know that it is not? No. Why are you angry? I don't trust the ID errors. It will be the same thing though, but this one is clearer. This one is comparing my partial evaluates. You see? That error did not exist. That's how I spent so much time just trying to debug that. For real. It's not common with whatsoever. Oh, it's common with whatsoever. I think it's just that Rust analyzer. Like that's the. Yeah. Like all this IDE help is all Rust analyzer. So every time you like save, Rust analyzer will compile your code for you and check for errors, then send it back to the IDE, and the IDE will now display it for you.
I think this particular issue of dice exclusively lines.
Yes.
It's mostly common with Rust Rover. It doesn't happen like that for PS.
Yeah. So that might not be a Rust analyzer thing then. Okay, so what is it supposed to return?
Another polynomial.
Yeah, what are the values?
Oh yeah, 0, 9, 0, 11.
Okay.
Yeah.
I call it vowels. So now it's becoming repetitive, right? It's like, so I'm just going to create a new one. To field, it takes like a vec of u64, right? I'm going to return a vec of field element. So it's going to do inputs dot into eta dot map v, then fr dot from v, right? and then we collect and return that. So instead of doing this here, we just do to field. Then likewise here. So you said what? 0? 0, 9, 0, 11. Those are just 12. Let's make a complaint a bit. I think there are errors. Okay. So it works. On the new poly?
No, the same poly.
Okay, so
Index 1 has 3. So, only the index. And then the result should be 09657. 15.
yeah, this thing might just, it's very irrational, but it works, right? So we have partial evaluate, which means we have multilinear. You said just like that.
Don't write lines and lines and you don't score, you don't use for.
I've done it before now. If you do it again, you'll be faster. Don't worry.
It's not even about the speed, it's about the number of lines you don't use to write what we use.
This is long. This is
The rest are comment.
So now let me show you what my actual you can see, right? So the same thing, right? We still checked the length, and then we returned the multilinear poly. And I have one for number of variables. I don't know why. But now still the partial evaluate. Partial evaluate is different here. So I'm taking the initial variable. That's like, let's say I had A, B, C, D. If I want to evaluate B, C, D at once, I'll pass in the index of B, but then my assignment will have 3 elements in it. So it knows that, oh, the first one is going to B, then I'll assign the subsequent ones to C and D. So it's sequential. The way Francis did his own is that instead of passing assignment as like a vec of F, he passes assignment as a tuple. So the index, comma, the value, index, comma, value, index, comma, value. So that way it's only you can do like random access. Yeah. So you can partially evaluate like A, C, and F at the same time. But mine is like straight, just like B, C, D. So mine is less expressive, but it's sufficient for like Sumcheck and GKL.
That is all. If you pass tuple,
Yeah.
and then you have evaluated at this and this,
Yeah.
and second time this will not be
The same index,
Yeah.
right? So you're going to subtract, we'll say 1 from the index depending on the position. So what it does is that it sorts first, so that it's always evaluating things that come before other things. So that for the next index, it just has to subtract 1, and next one it subtracts 2, on and on like that.
For you can do almost the same thing. Those are saying your own. If you want to make your own like your own like
You can,
rising with pass.
no, but mine is like the variables that you're assigning has to be consecutive.
So they have to go.
They have to be side by side. It's not random access. You can't skip. You get. It's not random access. But that's because of GKL, you'll be doing a lot of sequential partial evaluations at once. In the GKL protocol, it's going to be like, they just call it A. But then A is actually like 5 variables in your actual polynomial. So when you're evaluating A, you're evaluating 5 variables at once. So partial evaluation. So you just, your GKL is slow. So you call partial evaluate like for every single this thing, right?
No, I can call evaluate all of them.
But you don't have everything yet. So GKR is like, the polynomial is f of let's say f of b comma c, right? But that b is actually like b1, b2, b3, b4, b5, and c is c1, c2, c3. So there's when you're going to partially evaluate b, but you're not partially evaluating c. So your evaluate might not necessarily work for that. Evaluate wants you to have everything, right?
No, evaluate and let you skip. Like it's the same way you change it.
Okay.
You can have
So you can have none. Okay, then you're good then. You're good. Okay, so why do I have I here? Oh yeah, so there's an optimization. So if you're partially evaluating and the value you're evaluating at is 0 or 1, there's no need to do any linear interpolate and evaluate. I don't know if you get. Like, you're partially evaluating a variable, let's say A. If you're partially evaluating a variable and the variable is A, if A is 0 or 1, there's no need to compute. Like, that value is already in the Boolean. Let me write it out.
Oh, so you put it there. You put it there.
So this thing here is like, if A is 0, just return the left. If A is 1, return the right. So you know those 2 points, the pairs, is the evaluation at 0 and the evaluation at 1. So that forms a straight line. But then you can use that to get any evaluation at any other point. But if the evaluation is already 0 and 1, there's no need to do anything again, right? You just return left and right. So that reduces some computational steps. Make sense? Any questions? So let's move to Sumcheck. Oh, we need fiat chime. Huh? We do now. Yeah, I have not done it yet. I'll just copy it. Since Francis already did like a live walkthrough of fiat chime, there's no need for me to do a new one. Yeah? Okay. Say med, please. So I'm just copying this. My internet bad? Why? Yeah, that's what.
So what did that thing do?
I connected to a VPN. It was saying that my network was bad, but the internet is working, so I just felt like maybe I'd be a VPNs. Ish. Alright. So now we have the transcripts. And we have multilinear. I just copied the transcripts. So let's do some check now. Are we ready?
Yep.
Any questions, please? So we should do some check by hand first. Then we do some check. So let's do some check by hand. Any questions about like intuitions and all those things, please ask now as we are doing the sum check by hand. Yes, sum check by hand. So we'll do it coefficient form and evaluation form. So can someone give me a random? Are you guys not tired of that polynomial?
No.
2ab plus 3bc, right? So now, what's the first step of sum check? Yes. Okay. So let's do that. That's what? Yeah, we're evaluating the. Right? What will be the evaluation for this? Where's my eraser? Stress.
0, 0, 3, 0, 0, 2, 5.
Okay. Okay. So what's next? We sum, right? Cool. So sum check is now like the verifier didn't want to do this, right? So he said, prover, do this for me. Then prove to me that you did it correctly. So sum check hasn't started yet. Sum check is about to start now. It's not like, okay, the sum is 10. I'm going to prove to you that the sum is 10. That's sum check. So how does the protocol go? What's the next step? In very polynomial in the first variable. So that is, you keep a as a variable, and then you sum the rest of them over the Boolean hypercube. So this is what is actually happening when you do that, right? It's like f of a right? And when you're done with this sum, you're going to get a new polynomial called f of. So what is f of a 0, 0? It's 0, right? Then c is 1 now, but b is 0, so it's still 0. This one, b is 1. And then 1, 1. Right? So when we sum this, this is what? Right? So this is f of a. And then we send this over to the prover, to the verifier. So the prover is going to send 10, and it's going to send right? Then once that is over to the verifier needs to do the check. Yes. So this is like f of a at 1 is supposed to be equal to, so that's at 0 that's 3, right? And at 1 that's 4 plus 3. So the check passes. Now the verifier needs to get the next claim sum. But before it does that, it generates randomness. So it samples R Let's say r is equal to 5, right? Now this 10 is going to be updated by the verifier. So you're going to say the next claimed sum is going to be f of a right?
Is the verifier doing this?
Yes. So the verifier is the one that is doing this. The verifier is the one that's going to get the next claimed sum. Because I noticed that a lot of you guys were sending all the claimed sum
All the random.
from the prover, and you were sending that over to the verifier, which is wrong.
Really?
Yes.
The verifier only, the prover only send that first claim sum, that first one, and
The 10.
use the random to generate.
Yes. All the prover does is sends the first claimed sum, and then it just sends polynomials. Yeah.
So like the verifier doesn't need to send random.
No, we'll send it next. Are we good? Makes sense? Yeah. Yes. Yes. To get the next claimed sum. Yes.
And you're using that interpolate and evaluate.
No. And maybe. Yes. Yeah, that's evaluation form. That's what you're looking at now. Yeah. So what is happening when the verifier evaluates it at the random point? So you know that what did the prover give the verifier? The prover gave the verifier this, right? Right? So what is actually happening when the verifier evaluates a at r is that this place is replaced with 5. So that's not going to be like f of 5, 0, 0. And when you do this and you sum it, you're going to get, okay? Make sense? Okay. So this is what the verifier has been able to somehow compute. Now the prover is going to give the verifier the random challenge, right? So it sends it back to the verifier that r is equal to 5, or r1 is equal to 5.
I haven't done it.
So all it did is that it got the claimed sum for the next. You know, at the beginning. So the way Sumcheck works is really cool in the sense that there are steps to this. So at the beginning you have a poly and you have a sum, right? Which is equal to 10. This is what? Untrusted. The verifier doesn't trust this whatsoever. Now, the verifier does, they have this dance where they do a series of reductions. So, the verifier needs to make sure that the prover is doing each step correctly. So it's like, you know, the verifier is going to send a random challenge. And the prover is going to generate f of, so prover generates f of a, right? Now there's a link between f of a and that sum, right? That's like f of a evaluated at 0 plus f of a evaluated at 1 should be equal to 10. So they have created this link in such a way that the prover is not lying about this part, right? So this part is good. That's what that check, that 0 plus 1 check does. It ensures that going from 10 to f of a is good, but 10 is still untrusted. But going from that untrusted thing to f of a is trusted. Make sense? Then when it's done, it's going to send r, right? And then this guy is going to send in what? F of. He's also going to do that check. Make sure that you came down also in a trusted manner. And then you have what? He's going to do that check. Make sure it came down again in a trusted manner. But then you now use the oracle check. So now check the, then everything is now trusted.
That f of a equals to 5. My question is that the random challenge is 5, right? So, I don't know. The thing is that actually this f of a equals to 5. When I just sample the random challenge and an a is 5, I'm going to get like b and c.
As a prover or as a verifier?
As the prover, like I'm going to have b and c. Okay. So that b and c I can reduce it to c.
Can you repeat?
Like I'll reduce it to the variable and send it back to the verifier. The verifier can actually confirm as 0 and 1. So why are we evaluating at this 5 here now?
So you think that what the verifier confirming 0 plus 1 should be equal to? So you know initially it's supposed to be 10, right?
Yeah.
And that's what we did here. The next round is not going to be 10 again. It's going to be something else.
Yeah.
So that something else is the verifier that is supposed to figure out what that something else is. It's not that the prover will tell you what that something else is. Because if the prover is telling you what the something else is, and it's also the one that is giving you the polynomial, then it's almost like as if you have not done anything now. Like the prover says that, oh, the sum is going to be equal to 22. And I'm also giving you a polynomial that is like 11 and 11. You didn't achieve it. It's giving you both. You didn't achieve anything. You get? So the verifier has to be the one to compute what it's supposed to be equal to. That way it forces the verifier to give him something that's equal to that. But now this one, now the prover could be like, oh, I want this one to be 24. I want this one to be 28. But it doesn't matter because I'm the one that's giving you this, right? I'll just give you 14, 14. So that your round check is just useless. You get? So that's why I'm saying that the prover is not the one that's supposed to be giving all the claimed sums to the verifier. It's only giving the initial one, and then the verifier is going to get the subsequent claimed sum by evaluating each subsequent polynomial at the random challenge. And it's exactly the same thing, right? In the sense that when you give the prover R, what is the prover now going to do? The original polynomial, right? But now it's going to put 5 here, right? So what happens when you do this? This is basically like, so now that he has gotten it, he's going to get a new polynomial, right? Then what is he supposed to do with this new polynomial? It keeps B and evaluates C. So it turns it into 5, B is kept, right? 0. Then 5, B is also kept, 1. Now when this is what it's going to add this, right? And you're going to send this over to the verifier. What's the verifier going to do? At 0 and 1. B, right? So that means this one would turn into
5, 0, 0.
Right? And this one will turn into, then this one will turn into, and this one will turn into, and it's going to add it up, right? You're supposed to get 23. So the prover was honest, it's going to get 23, which is exactly the same thing that the verifier did initially. You get? So the verifier is capable of like computing all of this from just the f of a, which is that. Because at the end of the day, we still get that same structure, other than a being replaced with 5. So like, this is exactly the same thing. It's just that a is now 5. Yeah. Yeah, it doesn't. But you give the verifier f of a, right? But look at what f of a is. Right? Like this is what f of a really is. So if you evaluate at 5, then it's basically the same thing as replacing all the points where a is with 5, which is exactly what the prover and verifier are supposed to compute at the end of the day. Does it make sense? So Sumcheck is not going to, I don't know how to put it. Like, we're still discovering new things about Sumcheck every day. Like, more intuitions about it. It's like, it's useless. It feels useless. Like, why do you want to sum and why do you not want to prove that? It feels useless. And at the same time, it's not obvious how it works. So it's something that you guys have to just be going back to over and over again, just to develop like new intuitions for how it works. But right now, the mechanism is sufficient. Does that make sense? And if you have more questions about the intuition and we know how to do that, then we can just go over it. So when you send 5, it computes f of bc, right? That was 2ab, right? F of bc is f of a. Sorry. Right? Ten a plus what?
10D. Plus 3B.
So this is the f of bc polynomial. But now the prover is going to evaluate it at c, right? 0, 1, which is going to be so c is 0 here, so it's just 10b that will be left. What will be left now?
13B.
Right? So this is what is sent over to the verifier. Then the verifier is going to evaluate at 0 and 1 and ensure that it's equal to the sum. Which is equal to the sum that the verifier himself calculated, not that the prover gave him that sum. So that means this check passes. Then when you're done with this, you get a new random challenge, right? Okay? Then you now get the next claimed sum. The verifier gets the next claimed sum himself. So you can see that the prover doesn't really have anything to do with like sum. The claim sum doesn't care about that. All it just does is that it just generates polynomials for you. It just generates polynomials. It gets challenges and generates. The prover's implementation is so short. Like Sumcheck is mostly in the verifier. So your verifier is supposed to be way longer than your prover. Your prover is supposed to be like really short. It's the opposite.
Yeah, it's meant to be more than
So if I just scroll down, sorry.
If not, why is it verified?
I'm coming.
Just
Like this?
yes, sorry.
Why is it what?
Why is the verifier stressing himself?
No.
If he can just do the actual work for himself.
The lines of code
Yeah.
is not necessarily like direct proportional to how hard the work is. Like partial evaluation and evaluation, those are hard. But because we already have like functions for those, the prover's code is supposed to be like really short. Then the verifier is doing a lot of like, I need to verify the round poly, I need to do all of these things. Okay, good? So now we evaluate what 23b at what? At 4. What's 23 times 4? So this is supposed to be the next claimed sum, right? No, verifier just keeps it for himself. So to check. All the verifier is sending are the R's. That's all. Like it just sends the R's, the random challenges. Then all the prover is sending are the univariate polys. Yeah. Exactly. So the only thing you really need to put in your transcript is the initial poly initial sum. So those are the public inputs. Those are the things that both the prover and the verifier are supposed to know. So you put the thing that they are both supposed to know in the transcript. Then anytime the prover is supposed to tell the verifier something, you put that in the transcript. So it's like before in interactive, they're talking to one another, right? I'm going to say hi, and you say hello. But now, because of non-interactive, you are replacing that communication line with the transcript. So they are saying that, okay, rather than talking to me, the verifier, talk to the transcript. Do you get? And anytime you're supposed to hear back from the verifier, you squeeze from the transcript. Does that make sense? So put the public information and then put all the interactions into the transcript. That's like a mental model for how you know what you're supposed to put in the transcript. But it's really important that you put the public information. Most of the bugs that have been happening in ZK are mostly because people don't put the public information into the transcript. The public information. So let's say you didn't put like the polynomial, for example. Then it means that you could have been running Sumcheck on any polynomial, technically. Like you need to somehow constrain that we're running Sumcheck on this 2ab plus 3bc polynomial. If you don't do that, then the challenge is not going to be based on that. PHML is like the cause of bugs. So like I'm sure almost all the implementations that you guys have now might be buggy. That like it might be possible to generate a false proof that your verifier would accept. And you'll be like, yeah, you did it correctly. This ZK is crazy because of you might be getting hacked and you don't know you're getting hacked. Right? Because of it's just verify. It's so succinct. And imagine if you now have like billions of dollars behind a ZK system. You might generate a false proof. The verifier doesn't know that you generated a false proof. He just verifies it and it says that it's true. And then he gives you money. And then, there's no record. There's no nothing. That's why I feel like security in let's say ZK is going to be like really, really big. It's going to be really, really big. A new paper came out recently on GKR. Like a bug in GKR based on PHML. A bug in GKR based on PHML that nobody knew about all this while. It was during this cohort, like as we have been doing this, that's when the paper came out.
So is it possible that someone has taken like how many times?
So what is it might be possible actually, depending on how they implemented the system. It's ridiculous. It's ridiculous. Okay, so now the verifier is going to send R, right? Back to the prover. You need to keep track of it for the Oracle check, right? Because at the end of the day, you need to evaluate your problem at all the R's. Yeah, you need to save it in an array. Yeah. But the prover doesn't care. It just does what it wants to do with the R and forgets about it because it doesn't need it. So if your prover is storing challenges, just so that you don't need that technically. Okay, so when it does this, what is this? This is the R for what? For B, right? Yeah. So we're evaluating what? What's BC? This one, right? As B. So that'll be what? 10 into 4 plus 3. Is it 3? Yeah. Into 4C. So this is f of C. This is all the prover does. Like, see what the prover did in this round. He literally just evaluated this at 4, and it's done. No, the prover. Yeah, yes, evaluating at R's, and it's done. So now he just needs to send it. Yeah.
Sorry. No matter let's say the number of variables is 3. So for each number of variables given, the prover will be reducing it by one, till it comes to the last because it's only giving back the polynomial. So when he now reaches the last polynomial, let's say the last one like
F of C. Yeah.
Then he will now return it, then it's done.
It's done, yeah. So like now this is the end of the job for the prover. Yeah, the prover is done. No, we'll see when we're implementing how like short the prover implementation is. Right? They want to do is evaluate at 0 and evaluate at 1, right? That's 40 plus 40 plus 12, right? That's 80 plus 12. Was it 92 we had before? Okay. So it passes. And then we now do the oracle check. We need to teach you guys about Schwarzschild lemma actually. Schwarzschild lemma. Okay, because the oracle check is based on Schwarzschild lemma. How do you guys know Sumcheck and you don't know what Schwarzschild lemma is? You guys just memorize that, oh, oracle check is the last thing we need to do. You are memorizing the algorithm. You're like, oh, the first step we do this, the second step we do this, the third step we do this, the final step we do this. Huh?
Oracle check is like let's say the thorough check.
It's the final check, yeah.
Yeah, that's. I think what we are basically doing is like we're trying to, if some polynomials, like we're having like two polynomials.
Yes.
So if the polynomials are equal, then equal at any number of points that you pick, equal at any number of points. Whether you amplify it to like very large or whatever points, they will always be equal at those randomly selected points. But if not, they will not be equal in all points.
Almost all points,
yeah. Yeah, they can be equal in almost all, but they will never be equal at all points.
Yeah. So it's like, how do we do this? We should do it thoroughly. I'm thinking we should do it on Monday morning. Schwarzschild lemma.
First, you know, these things now, you know, like getting our answer on that with consistent.
Yeah.
So, I feel like things are there, I'm going to complication and stuff like that. Like having an error, like for this interaction, I think it's going to be like, it is almost impossible.
To have what? An error?
Yes.
Are you saying we should not do the oracle check?
I'm saying that what's the need for the oracle check? I can't get
It's
my
possible to have an error.
You're saying what's the need for the oracle check?
You can generate a polynomial that gives the same sum.
I'll show you the need for the oracle check. But just wait. Let's finish. Oh, well, so let's not do the oracle check. The thing you think is useless, right? So, what was the first one? That was 5, right?
Yeah.
The next one was what? 4. And then we choose like a random one, which is 3. And that's supposed to be equal to the last polynomial, and that's f of c, evaluated at that 3. Alright? So this is like Schwarzschild lemma, kind of. So this is exactly the same thing as this. I don't know how to show it, but it's actually exactly the same thing as this. It might not be obvious, but you know, we got this through like multiple, but at the end of the day, it's actually the same thing. You know, you started with f of a, right? You got f of a first, and you evaluated at 5. So that's like 5, then it's not obvious. 5bc, right? No, wait. Wait. I'm trying to see what the prover gave to the verified. The prover gave f of a, but 0 and 1 at the other side.
Yeah.
I'm coming. Sorry. Yeah.
Yeah, exactly. That's
Very important.
Well, we have backup, so hopefully. Okay, so it sent f of a, right? Which was just like f of a 0, 0, f of a 0, 1, f of a 1, 0, and f of a 1, 1. Right? But then next time, the verifier said that a should be 5, but b should be left alone, and then c should be. So this here is like f of a. Now what is f of b? It's saying that this should be 5 now, so it's fixed. But then b should be 0. No. B should be b. Right? This is f of b. The f of c is now saying that, oh, make b 4 and leave c alone. So this is f of c. This is what f of c actually looks like. So when the verifier now evaluates f of c at 3, all you're doing is that you're putting 3 here, right? So this is like, which is exactly equivalent. So unless like the prover did something wrong, maybe give you a wrong f of a, or a wrong f of b, or a wrong f of c, that's the only time that evaluating that at 3 would not be the same polynomial. And then when you now have two polynomials that are not the same, you can check that two polynomials are not the same using the Schwarzschild lemma. That's what it is for. That's like the main purpose. You're checking that, is this polynomial the same as this polynomial? But you want to check it really fast. So normally the way you check it is that you evaluate at all the points, right? And then see if it aligns there. But that's too much work. So there's the property of polynomials that allows you to just do it with just one check. And that shows the polynomial. But we'll go into more detail on Monday before we start GKR. So this should work.
So with that, not need that.
Might not need. No, you still. So like the point is that you're only checking once. The oracle check once. That's what Schwarzschild lemma allows you to do. But normally you'd have had to check it at like a ton of points. Does that make sense? Any questions? Let's implement. Huh? Sorry, I forgot you. Okay. Now let's imagine you had a polynomial, right? The polynomial is the same polynomial that we have always had, right? What's it? 0. Yes, this one. I'm going to give you a false proof, and you'll accept it. Okay? So the sum is supposed to be 10, right? I'm going to lie to you. The sum is 200. Alright? So I'm telling you now that the sum is 200. And I'm going to get f of a for you. So I'm going to send you 200, but I'm also going to send you f of a as 150, 50. Does that make sense? I'm sending f of a now. What would this look like as a univariate polynomial? I think it would be like yeah, this is evaluation form. But are you guys comfortable with evaluation form?
Yes.
Okay, then let's just use it like this. So this is the round poly I'm going to send you, f of a. So what are you going to do on your side? You're going to evaluate at 0, evaluate at 1, and make sure that it's equal to 200, right? So that's going to be what? 150 plus 50 should be equal to 200, right? Is it equal?
Yes.
So round check number 1 has passed. Then you will now generate a random R locally. So let's say you said R is equal to 2, right? Then you're going to evaluate this 150, 50 at 2, right? What would that be? This is why I didn't want to use.
Yeah, we can use that one.
Okay, so this is y1, this is y2, right? So that's going to be 150 plus 2 times 150 minus 50, which is 150 plus thank you. 2 times 100, right?
Yes.
This 130 or 150?
150.
It's my handwriting. So that's like 350, right?
Yeah.
So this is supposed to be the claim sum for the next round. I, as the verifier, as the prover, sorry, I know this was 150, 50 I sent to you. You will now send me the R, right? You said that R is equal to 2. Normally, I'm not supposed to do this, but I'm trying to deceive you. So what I'm going to do, I'm going to do exactly what you did, so that I can know what your claim sum is supposed to be. You get? No, I'm trying to deceive the verifier.
We want to do that.
Trying to see the verifier.
Change the
This guy
verifier.
is giving you back task to do that.
Yeah.
Will show you that you actually like.
No, so he is saying that we should remove the oracle check. So I'm trying to show him how I can make him accept if we remove that oracle check. So now R is equal to 2, right? I will do the same computation. So I will know that you are expecting the claimed sum to be 350. So then I'm just going to send you a new polynomial that's just, let's say, exactly. For example, right?
Why is sending me? No, no. There's always a process of sending me the
There's no
code.
follow.
I don't have to follow it. I as a prover can do whatever I want.
Okay.
It's only an honest prover that will do what the protocol is expecting you to do.
Is the prover a person that will just
Yeah, the prover,
You can write
the prover is a program.
People like over 18 years.
So I'm sending you 100 and 250, right? You're also going to do 100 plus 250, and you're going to get 350. And you'll be like, yes, this works, right? And then I'm going to get a new R. I'm going to say, okay, let's say R is equal to 1 this time, just so our competition is not crazy. Then you do what? 100
yeah.
plus
180.
you're expecting the next same sum to be 250. You send me the R is equal to what? 1. And then I'm not like, okay, I'll do the same thing. I know what your claim sum is supposed to be, 250. And then I just send you. This is the problem. So just the round check is not enough.
But if the initial claim sum is
Yeah.
correct, like for the, I don't know, like you know now, for the initial claim sum, you
Yeah.
give me a random stuff. Like a random number.
It's not a random number, it's sum now.
Yeah, it's a sum.
Uh-huh.
But if the initial claim sum is correct,
Mm-hmm.
do you still need, like now, the initial claim sum is actually like wrong. Do you still need the oracle?
So the oracle check is to make the protocol robust against both a cheating prover and an honest prover. If you don't have the oracle check, then you can't. I don't know how to put it. You are just like. You can be deceived, basically.
Just assuming that the provider
It's always honest. Yes. You're assuming the provider is always honest. But these ZK systems are. The ZK systems are guarding billions of dollars worth of value. People want that. So they are not going to be, if there's a hole, they will find a way. So they need a way to make sure that you need to be able to make sure that the protocol is robust to both somebody that is actively trying to undermine it and someone that is being honest. Do you get?
I'm going to go and read my own things.
Okay.
Like, what of this?
You're not convinced.
they're not confident.
Yes.
I just showed you.
Adi, this thing is like you're doing something at different intervals. Oracle check just goes like.
I get you, bro. I'll probably.
It's just like
So, do you know what you should do?
If something is
See, what you
continuous,
should do is write your prover and your verifier, right? Remove the oracle check. Yes.
he'll give you a
I will now give you a proof that your verifier will verify
But
with the wrong sum.
even with continuity, can actually can understand the fact that something is continuous at a point doesn't mean it's continuous at all points. So the fact that the person is giving you stuff at a point, like at different points, doesn't mean that it is continuous like at all points. So oracle check is like doing everything, like it's covering all the cases. What you're just doing is just at some points, not all the points.
All right. Let's go. Let's do this. So we have the proof. The proof is just going to be like the claimed sum and the round pulleys. So the round pulleys, I'm just going to use, I can use the univariate, like a vector of univariate pulleys. But my univariate pulley was not using F. But Fancy said he has made a PR. What would that be under? ZK something.
So you assume that the verifier and the prover knows the polynomial.
Yes, for now. But when you do like GKR, when you have added your polynomial commitment scheme, the verifier no longer knows the polynomial. Polynomial is hidden. I'm trying to see if like this transcript was named transcript, because that would now be like problematic. No, it was.
In my implementation, I'm returning the sharp polynomial as part of the proof.
Oh,
So I don't
yeah, you
have
could do
to
that.
just
Yeah.
erase.
So this is what I'm doing, right? Instead of using univariate poly, I'm just taking two field elements, right? The evaluation at 0 and the evaluation at 1 as my round poly. Does that make sense? So it's just the claimed sum and the round polys. That's all.
How about the initial?
I don't put it that way.
Like, how will the verifier?
I'll pass it in the proof function
The proof function.
and the verify function. Like it's way parameter
Oh, okay. The verifier function.
and the proof function. So we're good?
What you're doing here, you're creating a bound, a vector bound. Right?
Yeah.
More than two.
The round poly is always
Yeah.
2. So there's no need to have a vec, because then you now start doing checks. Like what if somebody sent you 3 or somebody sent you 4? But this one now is like you are using the type system to like enforce those checks. So now that we have the proof, the next thing we need is the proof. It literally just proves.
But this round poly is not supposed to be a vec of
Vector polynomial.
It's always a vec of polynomials, right?
and polynomial is a vec.
So, but the polynomial is like a line, right? The round poly is always 2 points.
I think it's a vec.
What is the type of your round poly? What kind of polynomial is it?
It's an evaluation point.
So you first half, last half, right?
Yeah.
2 points, right? What kind of polynomial is describable with just 2 points? A line. So I just have like a vec of 2 points. A vec of, how do I put it?
2 points.
Yes, 2 points. It's going to look something like this, right? So you're going to like A, B, another one, C, D,
Okay.
on and on like that. But I'm like forcing it to be 2. Are we
So
good?
if you put it in bracket, it will now become a vec of 2.
Yes, it's going to be vec of 2, which you could do also. That's also fine.
Yeah.
So we're going to working with like a multi. Why is it not recommended?
I've not added it.
I'm not ready to what?
The dev dependent.
No, but I think it's the mod. I still can't find it. Is it not pub?
I used to use it.
No, it's not pub. Yeah, that's why. Do you get? What methods do we make use of? I think it's fine. I guess.
You don't need to use all the.
No, it's fine. And the like claimed sum. So I'm taking the poly and I'm also taking the claimed sum. Then I'm returning a Sumcheck proof. Okay? So this is my prover. So the reason I'm doing this is that sometimes you already know what the claimed sum is. Especially like in GKR, you know what the sum is. You're just trying to prove that the sum is actually what the sum is supposed to be. So in that case, like it doesn't make sense for the prover to like sum the entire evaluation array. Does that make sense?
Sorry. If the verifier is also taking the initial array, there was a need for him to check if
Check
the
what?
sum, like the verifier is also taking in the initial
Polynomial.
What's the need to check if the initial claim sum is equal to the sum of, since they are also providing the prover with.
In the actual, you're saying that the verifier could just sum it by himself?
No, like here now we are passing in the claim sum.
For the proof.
For the proof. Now
Let me write verify. Alright, verify is going to take in the proof.
Yes.
And it's also going to take in the
Beside the
poly.
You're taking some polynomial and some.
So
Yes.
it also good.
Some is
So
inside.
yeah. So my question now is, the verifier is taking in the multilinear polynomial.
Yes.
The prover is taking in a claim sum.
Yes.
There's no need for that first check of checking in the sum of the poly is equal to the claim sum, because they are both seeing it.
Well,
like they are both seeing the values, they are both seeing the claim sum and the
yes,
and
but
the initial poly.
But the f of a might just be like a random f of a, right?
No, apart from the f of a, once you have gotten to that stage, that is different.
No,
I'm talking of the that initial.
No. The f of a evaluated at 0 plus f of a evaluated at 1 is supposed to be equal to this.
Yes.
So you need to check, because the prover could have given you a random f of a. You need to ensure that the f of a is linked to the claim sum. That's why that check is important. Because if you don't make that check, then you could have just given you a random f of a.
Then if that is the important check, then the other check that we did where we say the computation, the sum of the computation, the sum of the multilinear should equal the claim sum. It's not necessary there.
It was never necessary. That's like you're summing it on the prover side, right?
Yeah, on the verifier side.
On the verifier?
Yeah.
And that you're already doing what the verifier wants to outsource. The verifier is trying to outsource summing up all those things, right? So you shouldn't be doing that in the verifier itself.
But the prover can send in a wrong claim sum.
Yes. Then Sumcheck will not accept.
That is at the ending.
As Oracle check.
That is at the Oracle check.
Or any of the round check.
Okay. So you are saying it's okay to just go to the ending and fill down to like make down for the verifier to sum.
The verifier is not supposed to sum,
You don't want to sum at all.
That's the point of Sumcheck. Like, you do not want to sum the entire polynomial over the Boolean hypercube. You want someone else to do that for you. Yeah.
Okay. The multilinear polynomial can actually be very large.
Exactly. It's usually very large.
Very, very large.
Yes.
Just like
Yeah, it's usually very large. So the verifier doesn't want to do that.
But during the Oracle check, the verifier will do a lot of work.
It's only one evaluation. But you're like multiple. So that's where a polynomial commitment scheme comes. So a polynomial commitment scheme allows someone else to evaluate a polynomial for you.
So you're using two protocols.
Huh?
So you're using the Sumcheck and the
Polynomial commitment scheme.
Okay.
So the prover itself will be the one to now evaluate the polynomial for you. But then there's a way that the PCS will force the prover to not lie about the evaluation. So there's another protocol that can make the prover evaluate a polynomial for you, and you can be sure that it's not lying.
We are doing that one too.
Yeah, we're doing that too. It's a polynomial commitment scheme. There are multiple polynomial commitment schemes. So there's KZG, there's Fry, there's Fribenius.
Polynomial
Commitment.
Commitment.
Yes. So how the protocol works is that you have the polynomial. Before you tell the person where you want to evaluate at, the person will commit to that polynomial, which is like giving a fingerprint of the polynomial or something. Maybe a hash. But that's just the reduction. That's not how it actually is. But yeah, like a unique something that identifies that polynomial. Then it sends that to you. Then when it sends that to you, you now tell him that, okay, open that polynomial at this evaluation point. But then it gets the answer, but it also generates a short proof. So you now combine the fingerprint, the short proof, and the evaluation, and you run a protocol. and see whether it's true or false. If it's true, then the prover didn't lie about the evaluation. So that's what will be used here for the oracle check.
Okay, makes sense. Because I initially was saying it won't ask because it's always like the aim of the whole ZK stuff is
Not do too much.
verify to know something, to know the answer to something, without actually knowing actual thing that is causing that answer.
The steps. Yeah.
So basically, the verifier in this particular sum check, knowing the initial polynomial, is not full ZK.
It's not ZK at all, yeah.
It's not ZK at all.
There are two sides of ZK. There's the privacy part, and then there's the reducing the amount of work that you have to do.
Okay.
So if the verifier is even seeing the polynomial and maybe not doing anything with it, it might be succinct in terms of like the verifier is not doing too much work, but it's still not private because all the data is inside this multilinear polynomial. So there's something called like hiding and blinding factors that you can use to make your polynomials not sure, and then some PCS can hide things about the listing. Or we'll get there.
So the verifier taking in the initial polynomial, is it like something we still use in the other polynomial, or is just something you just want to do?
Right now we need it because we're not using a PCS, right? And the verifier will still need to do an oracle check. There's no way the verifier can do an oracle check without evaluating the polynomial.
Yeah.
So for now, we need the polynomial for the verifier.
Like, is it like?
And it's not different now, right? They're just putting it somewhere else, but at the end of the day, the verifier still has access to it. So that's just like data organization differences, but it's not different.
Okay.
All right. Yeah, you don't change anything. So that's now to the proof. To prove is literally just round right?
Yes.
So we need to generate for each round. We're doing evaluation form.
I don't keep track of the rounds.
I'll do it in a for loop for the number of rounds.
Okay, you do all of them at once. Go on.
Yeah. So I'm going to do fiat sharing. I'm going to do fiat sharing. So now, yeah, non-interactive. There's no need to implement interactive. Because we are doing interactive, that means that the prover and the verifier have to be online at the same time, and that's not always going to be the case. So you always have to like kind of like do non-interactive.
Can you simulate that to the test?
Yeah, you can simulate interactivity in a test. Yeah, but in actual production, imagine like you are trying to prove something, and the verifier has to be like online. Sometimes you're trying to prove one thing to like a bunch of people, so everybody has to kind of like be you prove to this person first, then come and prove to this person, then come and prove to this person. It doesn't make sense. So you just use fiat sharing to generate one proof, publish it, and then you just leave. Then anybody can just like verify that. Okay, so what are the public inputs? We know that the poly is public, and we know the claim. Right? So this one needs to go into the transcript. Does it make sense? I don't know. Right? So how do we push the poly? So I have append. What append does that it takes U8. So I need to somehow convert all the evaluations to U8 and then push that in here. Now, because what you are trying to commit to is not necessarily like, let's say, your struct or your multilinear struct, or what you're trying to commit to is like the information contained in the multilinear poly. And the only thing that really matters are the field elements. I don't know if that makes sense. Like that's what the multilinear poly really is the field elements. So that's what you need to commit to. But you can also commit to like the struct. It's just that both of them must know what. Just don't miss. Like it's okay to commit to more than you need than to commit to less than you need. Like let's say you committed to the first 5 evaluations, but then you left the remaining 3. That's bad. Because now the prover can adjust those three as much as he wants because it was never committed to.
What do you mean by committed to?
Like putting into the transcript.
Okay.
You can put more than you need, but never put less than you need. Because then you're giving the prover degrees of freedom that it's not supposed to have. Because you're trying to like constrain the prover's ability. Like you're saying that I want you to do this, then do this, then do this. If you give flexibility, then the prover might do things that it's not supposed to do. You get? So the problem now is like, how do we convert? I've forgotten how to do this. How do we convert to I want to convert a field element to.
You have to first convert to big int.
Okay.
Yeah.
So
Into big int.
I'm coming. I want to make this public.
Sorry, sir. Why are you adding a crate?
Why am I adding?
Crate.
Which crate?
Pop crate.
Also, I can access it from here. So I can access the evals from here. Okay. So I'm supposed to map this, right? So what I'm supposed to f dot what? F dot into
Yeah.
dot to bytes be, right? So what that will give me is give me like a vec of u8, right? Then I think I'm supposed to. Is this slice? No, I want to. So my append takes a slice. It takes this, right? This thing I've just done will return u8, a slice inside, then another slice inside for each field element, right? So what I need to do is I need to somehow collapse them to just one. So like if it was like 1, 2, then 3, 4. I want to like flatten it. I think that's the word.
I think there's a flat one.
Yeah, there's a flat map. Thank you. Yeah.
What does flattening is on?
What I just did here. Can you see this? I might not be see. Can you see this?
Yes.
So you have a vec of vec. So I want to just like remove the inner vex and just like write out the
Oh,
yeah. I need to collect first before I do a slice. The flat map?
Yeah, I thought it was correct actually.
No. So let me use the playground. So let's say we had this, right? For example, we can do like a dots. I think it should work. I'm not sure. Doesn't need iter. Then I can now collect it.
Wait, this looks like it's printed the same.
So what it did is that it just, this thing is lazy. It's rated as lazy. They don't actually do the work until you want to use the answer. Yeah. So this one now, it just like tagged it that this thing is supposed to be flattened. That's why it has this like flattening and so you're just putting the data inside. Then you would now like say collect or something, and then that's when it will now actually do the work. Yeah. So you flatten it. And it doesn't have to be the same length. Like this one could be like 5, 6. So you just flatten it. So that's what I wanted to use for this.
Also, flatten does not like put them in an array. I thought it would put them in one array.
Yeah, put them in one array. So
Now
this,
what's now correct again?
can you see the bottom?
Yes.
You can see the bottom. So this was like a vec of 2 vecs.
Yes.
The first one had 1, 2. Then the second one had 3, 4, 5, 6. But now we have just one vec that has 1, 2, 3, 4, 5, 6.
Yeah, you know, when you explained flattening the other time, you said it's like an array that contains 2 arrays.
Multiple arrays.
Yes, and then you remove those values and put them in one single array. So like my question is, if the flatten is already putting all of them in one array, why are we using connect again? Because I know connect is putting them in an array. So like if flatten is already putting them in one array, why are we using connect again?
Like if I remove the flatten now, right? Right?
Yeah.
This is what you will get. You see it?
So collect just joins whatever it sees.
Collect takes the stream and then puts it in one or whatever you're collecting into. But let's assume you're collecting to an array. So it takes the stream that's coming out from the iter and then it puts it into just one thing. What flatten does is that it changes that iter. So now the iter normally is supposed to just iterate over like the first vec, second vec, third vec. But flatten will now go into each of them, and the first thing to give out is 1. The next thing to give out is 2. And next one will be 3, 4, 5, 6. So collect is just putting those into the.
You shell them and put them in the
Yeah. So it's going to come in at 1, 2, 3, 4, 5, 6, and just putting them into like a vec. Does it make sense? Okay.
So
Yeah.
collect is what converts it to a vector.
No. Collect just takes a string and puts it in a vector. Is that what you're asking?
Yeah.
Okay.
Because you said vectors game.
Yes.
So you turn it to array and it prints an array.
Yes.
Why do you go on that score?
I don't.
You don't know the type.
I know the type, but Ross should be able to figure out the type.
That's why I didn't specify.
So I didn't specify it. Ross to just know that, oh, it's that, and then it just changes it.
So
Yeah.
basically what connect does is like flatten does the job.
Yes.
And leave it wherever it has done the job. So connect brings it back to you that did it.
Yes. So flatten is like, it's going to go, you have a vec of vecs, right? Normally, if you just iterate over that, it will give you the first vec as one item, then the second one as another item, and another item. So you only have like 3 outputs from your iter. But then if you now do dot flatten, instead of giving you the first vec, it will give you the first item in the first vec, then the second item and another. Then collect is just like putting it into just one listing.
So flatten will not put them in an array, to just connect those items.
Flatten is just a stream, yeah, it's not putting them in an array.
To not connect them, then
Yeah.
collect to now.
Then collect
Just
put
like
them in an
if you
array.
just did just did
Yeah.
now can you just collect? You still not do that.
Yeah.
Because collect is just like
No, but it doesn't really change anything, right? Like it's still like into iter.
Yeah.
It hasn't done anything. It just tagged it, yeah. It's just that we're not doing any this thing, okay. So now this is supposed to append the polynomial into the transcript. The evaluations. So we convert every evaluation to U8 bytes, and then we flatten it so that we just pass everything into the transcript. If we do this more than once, I will extract it into a function so that I don't have to like call it like this all the time. So what's next? The claim sum, right? Same sum is the field elements. Cool. So I've added all the public parameters. Then the next thing is just to generate all the round polys. So to generate the round poly, we'll have to do it like number of rounds, right? Make sense? So what are we doing each round? And we need the poly itself, right? So the first time we're supposed to what? Evaluate at, we want to get f of a, right? To get f of a with some, you guys understand the intuition behind that, right? But it's also the same thing as evaluating at 0 and evaluating at 1, right? So I'd rather use the evaluation at 0 and evaluation at 1. So I'll be like, round poly is going to be poly, the partial eval, the first element at 0, and then the evals, the eta, the sum.
Did I used to cram these things? I don't understand. Those Those know some words.
Slow down with it.
Today it was like,
Okay. So this is my round poly. Does it make sense that this is my round poly? Like the way you guys do it is that you break the evaluation into half, right? And then you sum, and then you sum. So I'm still summing, and I'm still summing. So this means that the top one must be the first half, and the second one must be the second half. So the question is now, can you see why the top one is the first half, and the second one is the other half?
But in this logic now, it's collecting evens and all.
Which odds?
I was thinking 36 we collect the first. I was thinking the first.
Let me show you guys.
Like 36 we take the first item. Then line 37 we take the second item.
You mean the first half summed?
Like the first item, like when this runs now, the first item, it's once this starts running in the array, the first item will be read by the first line.
What do you mean by first item?
If you have an array of say 1, 2, 3, 4, 5. I was saying like the first line we take like 1, the next one we take like 2 or something like that.
But now this is the round poly, right?
Yes.
And round poly always
Only has
two things, right? How are you generating your round poly?
Breaking it into 2, yes.
Okay, I'm listening now.
So, meaning this first one takes the first one.
The first half, yeah, and sums it, and the second one takes the
That's
second
like
half.
the even and the odd.
It's not really even and odd.
Like index, I was using like the index count, like.
No, that's more like.
Even, like, it's 0, 1, 2, 3, 4, 5. So the first one is like even number, second one is like odd number.
Yeah, but that's not how. When you take the first half, right? You're taking both even and odd indexes now,
yes,
right?
for the first time. But this one just have only 2 items.
It always has only 2 items.
If it has 4 now, will it take the first 2 or will it take 1 and 3? Like this one now, if it has 4, if the array has 4, will it take the first two.
You're saying if the round poly is
Yes.
is
Has
a
4 items.
that
Will it
is a degree 3 polynomial.
Yes. Will it take the first?
I'll evaluate at 0, I'll evaluate at 1, and I'll evaluate at 2. But I need to show why this evaluation is equivalent to taking the first half.
This is when it's not going to split and so inside. How is it breaking things?
Yes, that's what I want to show.
Index.
Guys.
There's something you did in your multilinear.
Yeah.
When you're checking if the value is 0 and 1, there's something they check you did in your multilinear. Please, I don't know if you can see. That's
Yeah, but I didn't do it in this implementation. I was showing you my old implementation.
Okay, the old one.
Yeah.
Okay.
But what I'm doing now is only efficient when I'm using the old implementation. But let me first explain this. Yeah. So look.
No, before you explain, there's something I wanted to ask.
Okay, yeah. What?
When you're committing your
Transcript.
Your what is it?
Polynomial.
Converting your this place transcript dot append. Sorry, your spelling is coming.
Yeah. I'm trying to make sure that OBS is okay. Yeah.
Yeah, you're converting your
Field.
prime field to byte.
Yes.
Is this not expensive? Like the whole iteration through everything to convert it to byte?
Yeah, but you have to commit your polynomial, right?
So the way I converted to byte, I didn't go through this iteration.
How do you do it?
I just created like a prime field to byte. Then I did the prime field, like the field dot into begin dot bytes big.
For every single evaluation, right?
Yes.
The same thing. It just looks weird, I guess.
So this flat map means flattening and map.
So these evals, right? Yes, it does. Yeah. So these evals, right? Don't mind them.
Just so straight, right?
Wait, Cass. So evals is like every single one of the evaluations, right? Then I'm iterating to get each one by one, right? Then I now do this. So this is like one of them. So I do f dot into begin dot byte be. So that converts that one to bytes, right? Then I'm using flat map so that everything is just one stream. Then collect the vec and slice. I feel like you have to always do this.
Yes.
One way or the other.
Yeah.
If not, you won't be given enough information.
Your evals, your poly dot evals, where is it? Where is it coming from?
It's coming from my.
So this is your multilinear.
Yeah.
So you add the polynomial to the transcript first.
I'm adding pronunciation transcript.
But the way you're appending it, it's not ordered.
It's.
You're just appending everything straight up at once.
You mean like what do you mean? Not orderly.
Like
Where exactly is it appended to the transcript structure? Can I see the structure?
For my transcript struct.
There's an appending here.
You just hash out the updates like you guys have. Yeah. And you said it's not orderly. Any problem?
So yeah, so what you just did all your evaluations and just appended them at once
To the transcript.
to the transcript.
Yeah. That's equivalent to.
All our for loops.
So no,
All our
inside each loop, right? I get
Inside each loop. How many loops do you have?
Sorry, inside the loop, inside my for loop.
Oh, you have a for loop.
Yes.
That iterates over.
So
So you're appending.
the number of variables.
That works too.
Yes, then that's where
Yeah.
I now
That works too. The goal is that all the information that's supposed to be in there gets in there one way or the other.
So the one is entering.
So me now is entering once.
So I want to confirm the order of entrance.
Yeah, so mine is it's still the same thing.
Yeah, it's actually the same thing because for the loop it's just
Starting from the exactly.
inside.
Yeah.
Okay, yes, that makes sense.
So what are you doing?
But you still use the loop now.
Huh?
You still use the loop.
I use iterators.
But this is
And that's the
this is like loop of loop.
Yeah, but the difference between mine and his is that it's calling transcript that append multiple times, right? For each field element. Now I'm only calling it once. After I've gotten everything as, but it's still technically the same thing. It might not be the same state, but it's still technically the same thing.
So this is what I'm looking at. So that means there are two loops here.
There's an iterator here, but yes.
Okay, I get it. So mine is one loop. So inside that one loop, this for loop now that is down here, that's where it's appending for all of them. So it's not looping to append separately and looping here again to do the rest of those guys.
The loop here is for.
No, I don't get.
So, now in this transcript of append, that iterator is actually performing a loop.
Yes.
So what I'm doing is, I'm not inside my for loop.
Yes.
Once you enter the for loop, it gets the univariate polynomial, append it there, does the
Univariate, right?
Yes.
Yes,
So
this is my initial poly.
Yeah, so this loop now that you have, this for I in is just one. Then inside that loop, that's where it does this append. So
But don't you do your initial poly?
my initial poly is outside, so
This
it resets it.
This is the reset. Wait, don't you append your initial poly to the transcript?
Like the first polynomial.
Yes, now.
At the top.
Yes, at the top.
Yes. Then you now inside the loop you append all the round
All the
polys.
round polys.
Yes, so it's same thing. So this one you are seeing here now is my initial poly, that's at the top.
Okay.
So now I'm still going to append this round poly
Okay,
to the
inside
transcript
here.
inside here also. You get? So that means that how are you appending your initial poly?
So my initial poly, what I do is, I have, okay, I see it now. I have a 2 bytes in my polynomial that
exactly.
goes through.
And then gives you a slice of you.
That's what he's doing.
Makes sense.
Alright,
So
alright.
what do you have to append then?
Yeah.
One for the transcript, one for the claim sum. But I could have put in one thing, right? Like I could have put the claim sum here also. It doesn't matter.
So like if it runs now, okay, if you don't know, right, it's the transcript.
You say?
No. It's, I've seen it.
Makes sense?
Yeah.
Alright.
What are you doing with that for? Like here?
This one here.
Yeah.
I'm generating all the round polys.
I like some out.
And so that's what I want to explain now. Why, no, this is equivalent to the half sum. But I don't want to start doing like len over 2 and slice and
So this works like that.
it works like that actually. So I want to show
But this
why
one
it works.
looks like it's more,
Computationally
yeah.
inefficient, yes, that's true. Depending on how you do it. Remember that trick I told you where you do, if it's 0,
If it's
you
0,
give left
yeah.
and if it's 1. So that's what will make this not inefficient. Do you get? If it's 0, like if you're evaluating, if you're partially evaluating at 0, there's no need to do that linear interpolate and evaluate. You already have all the points at 0. Do you get?
So I want to confirm something about the hash now.
Yeah.
What is the difference between, okay, let's say you have A and B.
Yeah.
When let's say I append A,
Yeah.
then append B,
Yeah.
then I put a hash. Is it the same thing as appending A and B together
Yeah.
at the same time and I'm putting a hash?
It depends on your implementation. It might not be exactly the same thing. That's like the states might be different. When you do those different things, states might be different. But the important thing is that all the information you're supposed to put in, which is A and B, has been put in somehow. Then the way you're putting it in is the same way the verifier is also putting it in.
So the verifier and program use the same transcript.
Yes.
Not the same transcript.
Not the same. Exactly. Like they both start with fresh transcript, and then they must do exactly the same process. Make sense?
Yeah, makes sense.
They're technically using the same transcript, but not like it's the same. Let's say Ross instant. Yeah. So how do I do this actually? Can I get a polynomial that has just two variables? Yeah. Alright, see this now. See this polynomial. That's the evaluate over the Boolean hypercube. Can you guys see this? I need you guys to focus on. So this is the evaluation of the Boolean hypercube, right? If you wanted to sum the first half, you would bisect it here, right?
Yeah.
Then you sum this to get, and you sum this to get. What I'm saying now is that there's a way to get this without bisecting. Like just partially evaluate A at 0. So you can see in this case, like all the A is here. And in this other case, all the A is here. So let's say we did 0B, right? That 2A would disappear, right? We're left with 15B. If you evaluate at 0 and 1, you see? So when I sum this, I'm going to get the same 15 sum. Then let's say we evaluated at 1. That will be 2 into 1, right? Plus 15b, which is what? 2 plus 15b, right? Evaluate at 0 and 1, that's what? 2 and, which is exactly the same thing as. And this also works for 3 variables. So if I evaluate this, let's say it had values. If I evaluate A equals 0, it's going to give me all these points here. And if I evaluate A equals 1, it's going to give me all these points here. So it's exactly equivalent to bisecting it in half. The reason why we had to go this route was when we're experimenting with not just Boolean hypercubes. I don't know, I think Francis talked about 3HC, right? Where it's no longer just 0, 1. Let's say 0, 1, 2. Now, if you want to get the round poly is supposed to be 3 values, not 2 values. This is the graphical representation. So 2HC is like this, right? 0, 1. If you want to do 3HC, it's no longer a straight line. It's now going to be something like this. A quadratic line. This is 0, this is 1, this is 2.
So that's like base 3.
Like base 3. But this is like one variable. If it's 2 variables, it's going to be what? But then this one is going to be something like this.
No, but each pages now have like 3 possibilities each.
Yes. Each variable has 3 possibilities each. So this is 3HC. Like, you know, in the other one, everything was a line. Now everything is a quadratic line. But then there's another one where everything can be like, what's next in after quadratic? A cubic line. So, as you are increasing the degree, you are changing the structure of the thing that's connecting the cube, or the square, or the point. Straight line. Yes. So we're implementing we're trying to create one polynomial that can turn into any of those. So now the round poly, for let's say this cubic one, is going to be 3 values, not 2 values. So that breaking into half is not sufficient anymore. So what we needed to do was to figure out another way to get the correct halves. That's when we now realize that, oh, you could just evaluate it at 0, 1, 2. So that's why it works, right? Alright, so now we have the round poly, right? So what do we do with the round poly? Huh? No, I've done it already. And this is the first, the round poly is like a vector of 2 elements. So this is the first element, and this is the second element. This is like the first half summed, and this is the second half summed. Is it clear? This is the round poly, right? Round poly returns a vector of 2 field elements. A partial evaluation is going to return all the places where A is 0 for this one, which is technically the same thing as the first half. Why this other one is going to return all the places where A is 1, which is technically the second half.
What does this partial evaluation?
No, it returns like evaluation formula, but it half the size.
Without like I now do dot evaluation.
But that means this will be more expensive than the one we were doing, the addition and so.
Most likely, yes. But if you have that trick that I was talking about, it will minimize the expense. This trick here. Like rather than doing that linear interpolate and evaluate every single time, if the thing you're evaluating at is already 0, just return the y1. And the thing you're evaluating at is 1, return the y2. So this will like make it less expensive. Okay, so now that we have the round poly, what do we do? We need to add it, we need to send it to the verifier technically, right?
Yeah.
So that means we need to add it to the transcript.
Yeah.
So this is now the second transcript add. How do we do this now? So now it's looking like we're repeating the same. It's looking like we're repeating the same thing. But I think we'll only do it once, so I think it's fine. Only twice, I mean.
Where's the flat map? Okay.
Can you not convert, since it's only 2 variables, can you not like convert them separately?
I could. Is that easier? That might be easier. But I'll still have to concat now.
You can just have that flat map.
You will say
Yes, that's how I actually did it. Like my multilinear poly can be converted to bytes. I'm coming. So round poly the flat map f. Why is there an error here? Oh, it's a fake error.
I think we have like a small helper function that takes it.
Yeah.
And just pass call the function passing this.
Yes. Yes. That would be better. Sorry. All right.
Yes, the difference is about it. So let's say the
So we have put the round poly into the transcript, which is almost the same thing as sending the round poly to the verifier, right? Then the verifier is supposed to send you back a challenge. So that's the same thing as squeezing sample field elements. So now I have the challenge. Now that I have the challenge, I'm supposed to what?
Yeah, but partial evaluator.
So we need to partially evaluate the original polynomial at the challenge. So that's just like poly is going to be equal to poly the partial evaluate.
We are still using that poly.
Yeah. What's the challenge? I think as F. I don't know what this samples. Three elements, yeah.
Yeah, I think that's like
Yeah, that's squeeze. The rapid squeeze. Then when you are done, you just return the proof. The claim sum, and then the round poly. So that's what the prover is supposed to do. I want to extract. Is it worth it? It might not be worth it. So all the prover is doing is we're always partially evaluating the first variable first, right?
Yeah.
So the first challenge will be evaluating A. When it's done evaluating A has disappeared. So B will now move forward to 0, and then C will now move to 1.
Because this is an index, okay?
Yeah. So then next time it's going to be 0 again, and then just continue like that. So does the proving make sense?
Yeah.
Now verification.
I thought the straight line was good.
Don't mind Francis. Don't mind Francis. It's supposed to be shorter than this, only because of I'm not using like multilinear poly dot to bytes.
Yeah.
So if I'm using multilinear poly dot to bytes, then this will like collapse down, and then this one will also collapse down. But then that's basically like
It's not 3.
it's not 3. Don't mind Francis. I'll tell you you're exaggerating.
So this round poly,
Yeah.
after evaluating, append
Yes. That's like me sending to the verifier. Anytime I'm sending something to the verifier, I find it in a transcript. And the verifier is supposed to send me
So where are we doing the random?
this squeeze.
Evaluating at the random.
Oh, this, yeah. The random distance challenge.
Ah, yeah, that's true.
So I guess that I'm just makes sense. Alright. So the verifier now. We have a proof and we have the poly. The poly is only going to be used at the end, right? The oracle check.
Yeah.
So what we really care about is just the proof. So the first thing we need to do is we need to add the public variables to the transcript, which is basically exactly the same thing as this, right? They both know the polynomial and they both know the claim sum. It's just that the verifier's claim sum is inside the proof. right? So now we have put all the public inputs in there. So the next step is we need to check all the round polys. If evaluates at 0 and evaluates at 1, and you sum it, should be equal to what the claimed sum is supposed to be, right? So the first one is one that we don't trust, that we just... I just copied it now. Like the transcript. Yeah, exactly the same thing. The public information is the polynomial and the claimed sum, so put that into the transcript. So the claimed sum is going to be the proof.claimed sum, right? This is the first one. So we iterate over all the yes. For round poly in proof dot round polys, right? We need to check that if evaluate at 0 and evaluate at 1 is equal to the claimed sum. So if
there's a way we can help the verifier to reduce stress.
How?
Before getting to the number of variables is supposed to be equal to the length of the vector of the invariant polys.
Yes.
So we can easily the number of variables is equal to the length of the invariant polys vector.
You have one round poly for each variable.
Yes.
Like f of a, f of b, f of c.
So we can just, at that first instance, before you even go down to the rest of the code, just check. Once it's not this thing, return false there and it's saved the verifier from the rest of the stress.
Right?
Yes.
So it doesn't need to waste time doing transcript and all this stuff. Yeah. Makes sense? So then if like the claimed sum is not equal to the poly.eta.sum, right? Then that 0, 1 check doesn't work. So you return false. Then when you do that, the next thing is to put the round poly in the transcript, which is exactly the same thing as this.
Yes, yes.
Rah. So we'll put the round poly in the transcript because we need both the verifier and the prover to do exactly the same thing. If not, we won't get the same challenges. So then once we're done with this, we need to now get the new claimed sum, which is like evaluating this round poly at the challenge. Right? Then new claimed sum. So claimed sum is now going to be equal to, so we need to evaluate round poly at the challenge, but now my round poly are two like field elements, so I'll just use that y1 interpolate this thing. So round poly bracket 0 plus challenge times right? So the claimed sum has not been updated. So the next time we'll get the next round poly 0, 1, it should be correct, and we should continue that all the way. Where is it? No. The claimed sum can be gotten by the verifier by evaluating the last round poly at R. The initial one. So see my proof is just like the first claimed sum. The Sumcheck. Prover. Improve, yes. Is that? Yeah, I'm not looking for anything at all other than just like returning it there. So now that we're done, we forgot to add the challenge, to start the challenges, right? No, we're not. Now We're almost done. Right? So let's keep trying to challenge so that we can do the oracle check.
We're not looking here.
Huh? We're not looping in the verifier. We're looping over every round pulley. So we'll do like challenges. Right? So this way we now have all the challenges. So now we just need to evaluate the round pulley. Yes. So we're going to say like if the claimed sum, so you know this claimed sum will be like f of c, is not equal to pulley dot evaluate challenges or return false, else return true. Now we fight. Is it? It's not a vex. Yeah, that's why I put this ampersand there. It's kind of like convert into a vex slice. What is it? Yeah, I can read the vex directly. But then a vex will move the information into the function. So if you want to use it again, then you have to clone. But if you don't want to use it again, then it's fine to just pass it in. What are we passing, sir? Challenges. I don't need to use it again now. But the problem now is that it's evaluate. Evaluate doesn't know that you're running Sumcheck. But you could have used evaluate in any domain. Could have been Sumcheck, GKR, Shaman, whatever. So it needs to be able to adapt to it. Wait, let me fix this error. What's going on? Don't mind my roster rise. It's probably my does it not know it's filled? Yeah? Oh, that's true.
But why do you choose Rust over?
I was in your Vim now.
New Vim. I'm not using the Vim.
I was here before.
Please, can you tell me your configuration for new Vim?
Okay.
I'm coming. I'm trying to fix a bug. All right. So we're done. We need to test now.
Where's the oracle?
Which oracle?
91 Line 91 on it.
Oh, my oracle check, are we? Yeah, it's here. But I don't know. We need to test it. All this one is just bobo. We don't know. For yesterday's our touch, are we?
I hope it was recording actually.
Bruh. Bruh. So, and we need to benchmark. That's actually very important. Okay, let's do this. How do we test this? Define a poly. Where is that old poly?
0, 0, 0.
3, 300.
25.
Oh yeah, what is the poly? Let's wait now. So you said 0?
30025.
I don't need to ask it every time. I just don't like exposing what I don't need to expose. So that I can get this to field. Yeah, I can just use pub. But pub is exposing it more than it needs to be exposed. Okay, so now we have our poly. The claim sum is supposed to be 10, right? So let proof equals prove the poly with 20. One problem at a time. That's rough thrower.
Using FR.
Yeah. Francis likes FQ. I like FR. And it was one that taught you guys. All of you now use FR. FQ. Huh? No, wait now. I've not done any assertion yet. It might fail actually.
I've seen proof from 20. I don't understand. Okay, I thought
This is the claimed sum, which is not actually the sum of the polynomial, right? It's supposed to be 10.
That's why I see why it needs to be passed.
Yeah, I need to verify it now. So we need to assert that. No, let me just print out the verification. We're expecting false. I can use that. You're supposed to use assert, yeah.
Yeah, but we'll print it out first to see.
Yeah. So is it the proof, right? No, the poly and then the proof. The proof, is it like a reference to? Not a reference to someone. So this should be, it should be false, right? If everything was done.
I used to know Vim that even when you want to append something in the middle of something, you start going from the result side.
It's still Vim. This is still, I still has Vim here. Like this is still Vim. Like I can still do all this kind of stuff. Vim is like a key. Is a key binding.
Vim.
What?
There was no way on your screen.
It's false. More.
The pressure.
More.
There's no, it's just like a movie comment.
It's false. So.
Just our poly correct.
The poly is correct. It doesn't even have to be. How do I put it? Like it can be any combination, but as long as 3 plus 2 plus 5. Oh. No, it's correct now. 3 plus 2 plus 5 is 10 now. Yeah. So something is wrong somewhere. Now with the bulb. Verify is the verify function.
The verify takes
Are you sure the force is not coming from 956?
Look how the verify takes it. Poly and double force.
Poly and proof. No, we'll figure out where it's coming from. This is the fastest way to the bulb. Where else are we getting false? So let's see where the false is coming from. It seems like it's the first one. No? It didn't show one. That cast wants sabotage me. Okay. But this is supposed to be correct. It's supposed to be like round poly dot length should be equal to the number of variables the number of variables. So that means that the prover must be doing something wrong, right? So let's print out the proof. There's no round poly. It's empty. So I was probably not pushing anything during the proving time, right? So where's my round poly? This is my round poly, but I'm not pushing it.
See, with that this thing, you don't even need to go down again. You're just...
My guy. Nice.
Let's go.
Passing wrong value.
Security guys.
What if the wrong value is actually right?
So you said 20, right? We're good. Now this is the most important part. I think I will stop the video, then I'll start a new one. Because the guys that are not here, they can just go straight to the second video, yeah.